Hello and welcome to the Aakash BYJUS JEE channel. My name is Atiullah and I'm back with a live session yet again on JEE Mission 2022. So before we begin, just let me know if you can see me clearly and you can hear me properly. And as soon as you give me a thumbs up and yes, I'm going to start this session. Alright, so guys joining in, Haritha, Viru, Captain Jack Sparrow, hello, good evening, how are you guys? How's it going? I hope everything is fine. Your preparation is going on full swing. Hello Shivam, very good evening. Shivam looks very excited with all these smileys. Excellent, I love the energy. All right, perfect. So you guys can hear me and see me clearly, which means we can get started with this session. All right, guys. So the topic we have chosen for this session is electromagnetic induction, which is a beautiful, beautiful topic. It's such a nice topic, such an interesting topic, and it is very, very scoring as well. Okay, very few concepts, very small concepts, and if we get that right, we are going to be in a position to score very well in JEE. Right, guys? So we're going to start this session on electromagnetic induction. And as always, the objective is to revise and the objective is to go below the layers and understand the concept. Alright, the concept is very, very important. Alright, so Thirumaran, Jyoti, Shalam all have joined. Very good evening, guys. And here we go with the first question. And as always, we're going to solve all the questions together. Alright, so here is the first question for you. Now, a metallic square frame of edge A is in a vertical plane. A uniform magnetic field B exists in the space in a direction perpendicular to the plane of the figure. The two boys pull the opposite corners of the square to deform it into a rhombus. So they are going to pull it and they are going to deform it into a rhombus. Okay. Now what is happening? They start pulling the corners at t is equal to 0 and displace the corners at a uniform speed of u. So they are pulling these corners at a uniform speed of u. So what do we have to figure out? The first thing we need to figure out is what is the induced EMF in the frame at the instant when the angles at these corners reduce to 60 degree, right? So earlier it was a rectangle, so the corner angle would be, it was a square, so the corner angle is going to be 90 degree. Now when they pull it apart, it is going to become a rhombus, and when this angle becomes 60 degree, we have to figure out what will be the induced EMF. Alright guys, so take a few seconds to absorb the question, understand it well, and let me know what is the concept that is involved in the question. First, I want to understand from you what is the concept we're going to use to solve this question, right? What do we have to find is the induced EMF at this instant. How do we go about it? I'm going to wait for your answer, okay? Because the solution, of course, is important, but the concept, the underlying concept is much more important. So we are going to break down all the concepts and we're going to understand all these things in detail. Alright, very interesting session ahead of you. So guys, as always, I love your participation, and here I want to understand what is the concept that we are going to use. I think the comments are not scrolling. Alright, so Captain Jack Sparrow is telling motional EMF. That's a way to look at it, but generally when we have a conductor moving with some velocity, then we go for motional EMF. Otherwise, it's we have a more fundamental law. Okay, what is the most fundamental law involved in electromagnetic induction? Okay, Math Solvers is asking, sir, how are you feeling now? I hope you are fully energetic. Thank you so much for asking that. Yes, I'm absolutely fine now and back with all my energy. Right? Thank you so much for asking that. All right, now back to the question. I want to know from you what is the most fundamental law that is involved in electromagnetic induction. What is that law called and what does that law tell us? Change in flux. Yes, change in flux. Go ahead, Captain. What happens with the change in flux? What is that law called? Come on, tell me, guys. So obviously there is magnetic field. So there would be magnetic flux through a closed loop. And whenever flux changes through a loop, what happens? Absolutely, Arshita has given the answer, Faraday's law of electromagnetic induction, the most fundamental law. So Faraday's law of electromagnetic induction tells me that the EMF induced is going to be minus d phi by dt. Okay, and what is phi? Phi is the magnetic flux. Absolutely, Captain. Math Solvers has also got that right. So we have to use Faraday's law of electromagnetic induction, which means I have to find this quantity phi. If I'm able to find this quantity phi, then I'll be able to differentiate it with respect to time, and I'm going to find the EMF. Alright guys, so let's try to do this. So let's say at a certain stage, this corner angle, okay, half of this corner angle has become theta. Okay, half of this corner angle has become theta. So what is my objective? My objective is to find out what is the flux. Okay, and here the magnetic field is constant. Okay, so the flux is simply going to become B into A, because the area vector is going to be along the magnetic field. Do you agree, guys? Okay, you know that the flux is the integral of B dot dA, but the magnetic field is uniform, and the area vector, which is going to be perpendicular to the plane of the loop, and the magnetic field is going to be in the same direction, so we can directly write flux as B into A. Is that right? Okay, so what is B? B is given to us, and what is the area? Now from this figure, can we find out what is the area? So this has become a rhombus. Can anyone tell me what is the area of a rhombus? Can anyone tell me what is the area of the rhombus? The area of the rhombus is given as, what is the area of the rhombus? Let me write it over here, is half d1 d2. Is that right, guys? And d1 d2 are the two diagonals of the rhombus. Okay, now if this is A, then we can say that this vertical line is going to be A sine theta, and this horizontal line is going to be A cos theta. Okay, so I'm going to write the area, and this is going to be half into d1 into d2. Okay, so what is d1? A sine theta is half of the diagonal. So obviously I'll have to double it. So I'll have to write it as 2A sine theta. And the second diagonal, the half of the second diagonal is A cos theta. So obviously I'll have to double it again. So I'm going to write it as 2A cos theta. Okay, so this 2 and this 2 is gone. 2 sine theta into cos theta is going to make it sine 2 theta. So what is this going to become? This is going to become BA square into sine 2 theta. Is that right? Alright, so the flux has come out as BA square sine 2 theta. Okay, now what do I need to do? I need to apply Faraday's law of electromagnetic induction. So if I have to find out the EMF at this point, I need to differentiate it with respect to time. Okay, so I'm going to write it as minus d phi by dt, and when I differentiate it, what is going to happen? Minus sign comes here, then BA square, and the differential of sine theta, sine 2 theta, is going to be 2 into cos 2 theta. So differential of sine 2 theta, 2 theta will become cos 2 theta, and the coefficient of theta is 2, so that will come out. Okay, so this becomes minus 2BA square cos 2 theta. Is that correct? So this is the EMF induced. Is that right? No, there's a mistake over here. Okay, because we are differentiating it with respect to time, not with respect to theta. So this is going to become into d theta by dt multiplied by d theta by dt. Is that correct? Is there any problem over here? Simple, we have calculated what is the flux at that instant, and when we differentiate it with respect to time, we are going to get the EMF induced. But the problem we are seeing here is that all these terms are fine, but there is a term d theta by dt as well. Okay, so now we'll have to do something about this term. What can we do about this term? Just look at the question again and think. Now it is given to us that this point, these points are moving with a constant speed of u. These points are moving with a constant speed of u, which we have not used in the question so far. So we will try to find out the relationship between theta and u. So let's try to do that. Okay, we'll preserve it, and then we are going to use it in the next part. Alright, now let's think about it. Now I want you to concentrate on this length. Okay, this angle is theta. What is this length? This is A cos theta. Okay, Now the rate at which this length is increasing, what length? I'm telling you again, what length am I talking about? I'm just talking about this length A cos theta. Now the rate at which this length is increasing, won't that be the speed of this point? Just think about it, okay? That length, the rate at which that length is increasing, so this point is fixed, this point is not going anywhere. So the rate at which that length is increasing is the speed of that point. Do you agree? So can I say that d of A cos theta, the length with respect to time, is going to be the speed? Do you agree? Right? So from here, what can we write? Let's differentiate it with respect to time. Remember, I'm differentiating it with respect to time. Okay. So this is going to become A. The differential of cos theta is going to be minus sine theta. And then with respect to time, so d theta by dt. And this is equal to u. So from here, what do we get? We get the value of d theta by dt. So from here, we get d theta by dt is equal to u upon minus a sine theta. And our problem is solved. Okay. Now let's go back and write this expression. What was this? Minus 2ba square cos 2 theta d theta by dt. So the EMF was minus 2ba square cos 2 theta d theta by dt. Now all we have to do is substitute d theta by dt over here and our job is done. Alright, so let's substitute it. So this d theta by dt is going to become u upon minus a sine theta. Okay, so this a and this a is gone, this minus and minus is gone. So what do we get? We get 2ba into cos 2 theta divided by sine theta. And there's a u here as well. Okay, now this is the EMF as a function of theta, but at what instant? Okay, at what instant is the EMF required? The EMF is required when this whole angle becomes 60 degree, correct? So this angle is going to become 30 degree. So what is theta? Theta is 30 degree. So we can substitute 30 degree to find the EMF at this instant. Is that right? So let's do that. So this becomes 2BAU, and then cos 2 theta, meaning cos 60 degree is going to be half, and then sine 30 degree is going to be half. This is going to get cancelled, and my final answer is going to be EMF is equal to 2BAU. Is that right? Any problem, guys? Is this absolutely clear? Okay, the game plan was very clear. We have to find out the flux, we differentiate it, we find out what is the EMF induced. Okay, a little twist in this question where we had to find out the relationship between d theta by dt and u. So that was something we were able to find out very quickly. So after doing the substitution at this particular instant, we get our answer as EMF is equal to 2BAU. Any problem, guys? If you have any confusion, anything you want to ask me, ask away and I'm going to answer that. Okay? Just check if you are comfortable with this. Alright, so if this is clear, let's go to the next part of the question. So what is the next part of the question? We have to find out what is the induced current in the frame. What is the induced current in the frame at this instant if the total resistance of the frame is R. Okay, so we have to find out what is the current. Okay, the total resistance of the frame is given to us as R. Okay. So we can say that the current, that's a very simple question, the current is going to be the EMF at that point, at that instant divided by R. Okay, so this is going to become 2BAU divided by R. So that is going to be our answer. The current at this instant is going to be 2BAU divided by R. Pretty straightforward. It is not asked in the question, but I'm asking you. Can you tell me the direction of the current? Can you tell me the direction of the current? And I'm going to wait for your answer. Can you figure out what will be the direction of the current? Any hints? Can you figure out the direction of the current? How do we figure out the direction of the current? Is there a law which tells us? How do we use that law? Can anyone tell me? Okay, so Abhinand is asking, where is the frame moving? See, the frame is not moving. See, the frame is not moving. The frame is only getting deformed. Okay, so this point is being pulled with a speed u. This point is being pulled with a speed u. So what is happening? This is the square. This is the square. This frame is not moving anywhere. It is just becoming a rhombus. Okay, so this square is becoming a rhombus. This is what is happening. Alright, so Arshita is saying right hand rule, Lenz's law, Lenz's law, Lenz's law. Yes, absolutely right. When we have to find out what is the direction of current, although Faraday's law also tells me the direction of current, but that's a bit complicated. So we use Lenz's law. Okay, so how do we use Lenz's law? The current is always going to oppose the change in flux. Okay, the current is going to oppose the change in flux. Now what is happening? Now the magnetic field is going inside. Can you see the magnetic field is going inside? If the magnetic field is going inside, okay, there's some flux. Now if we are making this, deforming this square, if we are deforming this frame, what is happening? Is the area increasing or decreasing? The area is decreasing. This is going to become like this, and finally it is going to become a straight line. So what we see is that the area is increasing. Now if the area is increasing, the magnetic flux is decreasing. Okay, so what will the current try to do? The current will try to increase the flux. Okay, the current is going to try to increase the flux, which means the current is going to produce a magnetic field going into the plane of the screen. Okay, the current would be such that it produces the magnetic field going into the plane of the screen because it wants to increase the magnetic field. The flux is decreasing, the current wants to increase the magnetic field, and hence it is going to go in a manner, it is going to flow in a manner such that it creates its magnetic field going into the plane of the screen. Is it right? Because it wants to increase the magnetic field. Okay, so how can we see that? Okay, so I'm going to turn in this direction so that my left and right doesn't become confusing. Okay, so we want the magnetic field going into the plane of the screen. So the current is going to go clockwise. Is that correct? The current is going to go clockwise so that the magnetic field is going to go into the plane of the screen. So in this question, the current is going to be clockwise. Okay, that is how we use Lenz's law to find out the direction of current. Okay, is that clear? Is that absolutely clear? Any problem here? Absolutely, Arshita is absolutely right. It is going to be clockwise. Abhinand is right. It's going to be clockwise. So we use Lenz's law in this manner to find out what is the direction of current. Alright, perfect. So now let's move to the next part of this question. Okay, what is the next part of the question? We have to find out what is the total charge which flows through a side of the frame by the time the square is deformed into a straight line. Okay, so at one instant this square is going to get deformed into a straight line like this. It is going to get deformed into a straight line like this, and we have to find out what will be the charge that has flown. Okay, now obviously current is flowing. What is current? Current is flow of charge. So in this time we want to find out what is the charge that has flown through this loop. Is that correct? Okay, and what we are interested here is the net charge flown. Okay, so how do we find out the net charge flown? We are not talking about the charge flowing at that instant. We are talking about the net charge that has flown. So what we are essentially talking about is the average current. Now the average current is given by delta Q by delta T. Is that correct? The average current is given by delta Q upon delta T. So this delta Q is the charge that has flown in time delta T, and this quantity is the average current. Is that clear? Okay, perfect. Now what we also know is that the current is minus d phi by dt divided by R. Okay, so what is the EMF? Or I should write it as EMF. Okay, so the current is EMF upon R. Is that correct? So whatever is the EMF induced at that instant divided by R is going to give me the current. Okay, now this we are talking in terms of instantaneous quantities. Now if I want average current, can I write it as the average EMF divided by R? Is that right? So if I talk about average current, I can write it as the average EMF divided by R. Correct? Okay. Now what do we have here? We have EMF is equal to, and I'm just concerned with the magnitude, so I'm writing d phi by dt. I'm just concerned with magnitude over here, so I'm dropping the minus sign. So the EMF is d phi by dt. The magnitude of EMF is d phi by dt. But this is an instantaneous quantity. If I want E average, then what can I write? Okay, can I write it as delta phi by delta t? Of course, I can do that. Is that clear? Okay. So average current, what can I write it as? It is E average upon R, which I can write it as delta phi upon delta t into 1 by R. Is this clear? Here we are not talking about instantaneous quantities, but here we are talking about the average quantities. So delta Q by delta T, I can write it as delta phi upon delta T into 1 upon R. Do you agree? Any confusion? If that is clear, then delta T and delta T is going to get cancelled and delta Q is going to be delta phi upon R. Do you agree? Plain and simple. So what we have found out is that the charge flown would be the change in flux divided by R. Now finding the change in flux is very simple, okay? And we are just concerned with the magnitude, so we don't need to worry about plus and minus. What was the initial flux? The magnetic field was B and the area was A square. What will be the final flux? The final flux is going to be 0 because it becomes a straight line, so the area is 0. So the change in flux is going to be B A square divided by R, which tells me that the charge flown is going to be B A square divided by R. Is that clear? Okay. So that is it in this question. There were 3 parts, all very good parts, but the important thing, there are so many important concepts we covered. Number 1, Faraday's law of electromagnetic induction we covered. Second, we covered Lenz's law. And third, we also covered the relationship between the average quantities. Okay, what is average current, average EMF, what are those quantities? So it may happen that we don't have to deal with instantaneous quantities, but we may also have to deal with average quantities. Alright guys, is this clear? Is this absolutely clear? And if it is, let's move on to the next question. Alright, let's go for the next question. Meanwhile, if you have any confusion anywhere, don't hesitate to ask me. Alright, let's go for this question. Now we have a right angle triangle ABC made from a metallic wire and it moves at a speed of V. So this entire wire, okay, is moving with a uniform speed V in its plane. There is a uniform magnetic field B in the perpendicular direction. So as you can see that the magnetic field is coming out of the plane of the screen. Find the EMF induced. Okay, we have to find out what is the EMF induced. Cool? Is the question clear? Now I'm going to tell you where we have to find the EMF induced, but is the situation clear? Okay, I hope the situation is clear. Okay, so the first thing we have to find out is what is the EMF induced in the segment BC. Okay, what is the segment BC? This is the segment BC. We have to find out the EMF induced in this segment BC, and then we have to find out the EMF induced in this segment AC. Okay, now you tell me what is the fundamental concept behind this question. Can you tell that? What is it that we are going to use over here? Okay, because the most important thing about these sessions is that we need to revise the concepts. Okay, Arshita and Captain Jack Sparrow is saying motional EMF. Absolutely guys, absolutely motional EMF. So I should give you a little revision of motional EMF. Okay, now in a situation where the velocity magnetic field and the length of the wire all are perpendicular. Okay, and obviously we are talking about a uniform magnetic field. Now this is very, very important to know the relationship between the angles between the velocity, length and magnetic field. Now if the velocity, length and magnetic field are all perpendicular to each other, then the EMF induced is BVL. Obviously I cannot go into the derivation over here, but this is what we know. Okay, EMF is BVL. Okay, now in a situation where the velocity makes some angle, okay, let's say the magnetic field and the length are perpendicular, but velocity makes some angle with the length. Okay, in that case what happens? We break down the velocity, we break down the velocity into two components. So this would be called V perpendicular and this would be called V parallel. So what does V perpendicular mean? V perpendicular means that the component of velocity perpendicular to the length. Okay, so in this situation we say that the EMF is going to be B into L into V perpendicular. The parallel component of the velocity does not contribute to the EMF. Okay, the parallel component of velocity does not contribute to EMF. Only the perpendicular component of velocity and perpendicular to the length, that component of velocity attributes or contributes to the EMF. Is that correct? Okay, perfect. Now let's talk about BC. Let's talk about the segment BC. Now here the velocity, the length and the magnetic field all are perpendicular to each other, which means that the EMF is going to simply become BVL. Do you agree? Any problem? Perfect. All right. Okay. Now we also have to talk about segment AC. Now for segment AC, what do we see? That the velocity is going to be like this. The velocity is going to be parallel to the length. There is no component of velocity which is perpendicular to the length, which means that the EMF induced in AC, the EMF induced across AC is going to be how much? It is going to be BL into 0, because the perpendicular component of velocity is 0. So this is going to become 0. Is that clear? Any problem here? So the EMF induced in BAC is going to be BVL and the EMF induced in AC is going to be 0. Perfect. All right. I hope this is clear. Now we want to calculate what is the EMF induced in segment AB. Okay, this is segment AB. Cool. Okay. Now what is the velocity like? The velocity is like this. So obviously what we'll have to do is we'll have to take the components of velocity. So let's say this angle is theta. So this angle is also going to become theta. So this is going to become V cos theta and this is going to become V sin theta. So what is the perpendicular component? The perpendicular component is V sin theta. And let's say this length is L prime. Let's say this length is L prime. So the EMF induced is going to become BV sin theta into L prime. Do you agree? BV sin theta into L prime. But if we look at this right angle triangle closely, if we look at L prime sin theta, what is this? This is 90 degree. This length AB is L prime. So what will be L prime sin theta? L prime sin theta is simply going to be L. Okay. So E is going to be BVL. Is that correct? Any problem? Okay. So I hope this is clear. But what I also want to know from you, is in the wire BC, which side is going to be at positive potential? Is B going to be at positive potential or C going to be positive potential? So basically a moving wire, we can treat it as a battery. So either the battery can be like this, where B is at positive potential and C is at negative potential, or the battery can be like this. Which of them is correct? Can you explain that to me? Okay. Which is going to be at a higher potential? And how do we figure that out? Okay, Gitanchu is saying, sir, video quality low hai. I think it's fine for everyone. Gitanchu, you can refresh your screen and then check. Alright, Arshita is saying that B should be at higher polarity. Alright, let's see. Let's see. So the thing here is that the force on the positive charge is, the force on the moving charge particle is QV cross P. Okay. So if we are talking about positive, let's say, so the cause of EMF is the electrons. So Q is the negative charge, correct? So what we have to do is we have to do a V cross P. Okay, we have to do a V cross B. And how do we do V cross B? So I'm going to turn so that I'm seeing you. Okay, so the direction of V is going to be from right to left according to you. Okay, from right to left. That is the yes, from right. So no, I'm sorry, it is going to be towards right. Yeah, this is going to be towards right, and the magnetic field is going to come out of the plane of the screen. So if we do a V cross P, then upward is going to give me the Right, so this is V, and B is going to come out. Okay, B is going to come out as per U. So if we do a V cross B, then this is going to give me I am sorry, I think it becomes a little confusing when we change sides. Okay, so I'm going to try to do it as per you. Alright, so according to you, V is going to be like this. I'm very sorry. Okay, V is going to be towards the right, B is going to come out. Okay, so when we do a V cross B, it is going to be downwards. Okay, so the V cross B is downwards, which means the force on the negative charge is going to be upwards. So electron is going to go up and positive charge is going to be accumulated down. Okay, so this tells me that the battery is going to be like this. C is going to be at a higher polarity. Okay, so the simple rule is you do V cross B, and whatever is the direction of V cross B, that direction is going to be at higher polarity. That is going to be at positive polarity. Is that correct? So for BC, the positive polarity is going to be at C, and for AB, the positive polarity is going to be at A. Is that correct? Is this concept as absolutely clear? Yes, Captain Jack Sparrow is absolutely right. C is positive. Arshita is also right. C is at higher potential. Perfect. So I think you guys have got it. Okay. Now let's go to the last part of this question. And the last part of the question is find the induced EMF in the loop ABC. So we have to find the induced EMF in the entire loop. Okay. So there are two ways to look at it. Number one, we have already calculated the EMFs. Okay. So C was at higher potential. So this was BVL. We can replace this by a battery. And then A was at higher potential. So we can replace this by a battery as well. Okay. So BVL, BVL. Now both the batteries have the same EMF, but their positive sides are connected, which means they are going to act in opposite manner. They are act in opposite manner, which means the net EMF is going to become how much? The net EMF is going to become 0. Is that correct? Another way to look at it was that what is the flux through this loop? Now the magnetic field is uniform and the area of the loop is also uniform. So when it is moving, the flux through the magnetic field through the area is not changing. So the flux through this loop is also not changing. And if the flux is constant, then obviously d phi by dt is going to be 0 and EMF is going to be 0. Is that correct? Okay. So there are two ways to look at this question, but it becomes very clear that the EMF is going to be 0 no matter how we look at it. Okay. Captain, as always, is absolutely right. No changes in flux, hence no changes EMF. Perfect. So if this is clear, now we are good to go to the next question. Alright, here is the next question for you. This is a slight variation of motional EMF when a rod rotates in a magnetic field. Okay, what is the question? Now the length of the rod is 10 centimeter. It is made up of conducting and non-conducting material. Okay, the middle part is non-conducting. The rod is rotated with angular velocity 10 radian per second about the point O in uniform magnetic field of magnitude 2 Tesla. Find the induced EMF between points A and P. Okay, we have to find out the induced EMF between these points. We don't have to find out the induced EMF between A and O. We have to find the induced EMF between A and B. And some part of the rod is conducting, some part is not. Okay, that's the question. Take a few seconds to absorb the question and then we're going to talk about the solution. But as always, I want to know from you what is the basic concept involved. How do we deal with a rod which is rotating? Absolutely, Captain is on fire today as always. Integration. Okay, and the reason is that for a rod, the EMF induced is BVL. Okay, but here when in this situation when the rod is rotating, different points have different velocities. So this velocity V is not constant. Okay, so we cannot directly write a formula for this. So what we'll have to do is we'll have to break this rod into small pieces, find the EMF across those small pieces and then add them up. That's the way to go about it. Perfect. So let's try to understand this. So this is the point over here. Okay. Now let's say we take a small length. Okay. This length is dx. So at a distance x, we take a small length dx. Okay. Now this rod is rotating with angular velocity omega, which means the velocity of this small part is going to be omega into x. Do you agree? Okay. Now what will be the EMF, the small amount of EMF induced across this point? Okay, across this length dx, the small length dx, what will be the EMF induced? The EMF induced would be BV into the length. And what is the length here? The length here is dx. So this is going to become BV dx. So dE becomes B into omega x into dx. Is that correct? Okay. Now here what we have to do is we have to find out, let's say this is L1 and this is L2. So we have to find out the EMF induced between L1 and L2. Okay, this is L1 and this is L2. If the question was to find the EMF induced between point O and this point, then the limit of integration would have gone from 0 to L. But in this situation, the limit of integration is going to go from L1 to L2. Is that clear? So depending on between what points the EMF is required, you can find out what will be the limit of integration. Okay, so the limit of integration here is going to go from L1 to L2. Okay, so the net EMF is going to be the integration of B omega x dx, and the integration is going to go from L1 to L2. Is that correct? From this diagram, can you see what is L1? L1 is 7 centimeter, and what is L2? L2 is 10 centimeter. Is that right? Alright, so it's a simple integral. Let's do this integral. So this is going to become B omega, and the integral of x is going to become x square by 2. You put the limits, it is going to be L2 square minus L1 square divided by 2. Okay, now all we have to do is substitute and we'll get the answer. So magnetic field is given to us as 2 Tesla, omega is given to us as 10 radian per second, and then we have a 2 over here. L2 square, okay, this is given in centimeter, so we can write it as 10 into 10 to the power minus 2 meters square, minus this is 7 centimeters, so we can write it as 7 into 10 to the power minus 2 square. So what does this come out to be? 10 to the power minus 4 is going to come out. This is going to become 10 to the power minus 3, and in the bracket we are going to have 100 minus 49. So what is that going to be? That is going to be 10 to the power minus 3 into 51. So the EMF is 10 to the power minus 3 into 51. So that is going to be 0.051 volt. And that should be my answer. Is that correct? Is this clear? Any problem? Hello Martin. How is it going? Okay. I hope you are able to follow what you are doing, and I would absolutely love your participation in the questions that we are doing. Alright guys, so is this clear? Now in this situation there is a result that you should remember. Okay, this was a special case, so we had to integrate from L1 to L2, but if we have to find out, and if there is no non-conducting part, if every part is conducting, and then let's say the length of the rod is L, and we have to find out what is the EMF induced across O and A, then we can directly use E is equal to B omega L square upon 2. Okay, this is a result we should remember as well. Okay, so in a typical case, we should remember B omega L square divided by 2. But the concept is important. If the typical situation is not given, then we should not be dead ducks. We should be able to figure everything out. Alright, perfect. So if this is clear, let's go to our next question, and here is the next question for you. Now we have a wire PQ, it has a mass M, resistance small r, and can slide on the smooth, very long horizontal parallel rails separated by a distance L. The resistance of the rails is negligible. A uniform magnetic field B exists in the rectangular region, and resistance R connects the rails outside the field region. Okay, at t is equal to 0, the wire PQ is pushed towards the right with a speed V0. Find. Okay, so we'll talk about the question, we'll talk about what are the things we need to find out, but first let me know if the situation is clear. Let me know if the situation is absolutely clear. Okay, so we have this metallic wire, it has a mass m, it has a resistance also, it has a resistance small r as well. The length is L and it is sliding on parallel rails. The magnetic field is perpendicular, it is uniform, and then we have this external resistance capital R which is out of the magnetic field. This is the situation. And then what do we need to find out? We need to find out what is the current in the loop at the instant when the speed of the wire is V. Okay, so what is the speed of the wire? The speed of the wire at this instance is V. So we have to find out what will be the current at this instant. Okay, very simple. So this is a question on motional EMF, is that right? So the magnetic field, the velocity and the length all are perpendicular to each other. So the EMF is going to be BVL, correct? But I also want to know what is the direction of positive polarity. Will P be at positive polarity or Q will be at positive polarity? Can you figure that out? Will P be at positive polarity or Q will be at positive polarity? Can you figure that out? Alright, I'm waiting for your answer. P is at positive polarity. Are you sure, guys? The magnetic field is coming out of the plane. The magnetic field is coming out of the plane. Yes, you're absolutely right. Okay, so V is like this. B is going into the plane. So V cross B is going to be up. Absolutely. So P is going to be at positive polarity. But when we are replacing this rod, then we should introduce an internal resistance also. Okay, so the resistance of the rod is smaller. We are going to treat that as internal resistance. Okay, now this loop is complete. If this loop is complete, then what will be the current? The current is going to be the EMF, which is BVL, divided by the total resistance. So the total resistance is going to be capital R plus small r. Okay, so the current is going to be BLV divided by capital R plus small r. Okay, a very simple question to start with. This is the current at this instant. Alright, now let's go to the next part. Now in the next part, we want to find out what is the acceleration of the wire at this instant. Okay, so what is the current? The current is going to flow like this. Okay, this is the direction of flow of current. Now we have a current carrying conductor which is moving in a magnetic field. And if we have a current carrying conductor moving in the magnetic field, obviously it experiences a force. Okay, what is that force? That force is ILB. So I'm simplifying it and writing it for you. The magnetic field is constant and the length is perpendicular to the magnetic field. Okay, otherwise you know that the force is IDL cross B and the integral of that. Okay, that's the net force, but we have simplified it because the magnetic field is uniform, the rod is a straight current carrying conductor, and the length between DL, L and B is 90 degree, so we directly get F is equal to ILB. Is that correct? Okay, can you tell me what will be the direction of force? Is the direction of force going to be towards the right or the direction of force is going to be towards the left? Okay, the force on the wire is going to be IL cross B. Can you tell me what will be the direction of force? Absolutely, Pratham. Awesome. The force is going to be towards the left. Okay, the force is going to be towards the left. And you can simply do L cross B. So basically the direction of L is the same as the current. Okay, so if you do an L cross B, you will see that the force is going to be on the left. Absolutely. Okay, so let's find out what is the magnitude of force. The magnitude for force is ILB. Okay, and what is I? I is BLV divided by capital R plus small r. Then we have to multiply it by L into B. So we are going to get acceleration as, okay, this is the force, and force can be written as mass times acceleration, and then you divide it by acceleration. Okay, so the acceleration will come out to be B square L square V upon M into capital R plus small r. Perfect. Is that clear? So the acceleration is going to be towards the left and the velocity is towards the right. So we'll have to keep that in mind. Okay, what is the next part? The velocity as a function of x. So we have just found out that the acceleration is B square L square V upon M capital R plus small r. And remember, the velocity is towards the right, the acceleration is towards the left, which means we can write A is equal to minus of this quantity. Do you agree with me or not? Okay, so acceleration is opposite to velocity, so we'll have to introduce a negative sign. Is that correct? Is that clear? So whenever acceleration is opposite to the velocity, we say this is deceleration. So that is why we have written A as minus B square L square V upon M capital R plus small r. Okay, now what do we have to find out? We have to find out V as a function of x. So there's no point introducing time over here. We have to find out V as a function of x. So acceleration, we can write it as V dV by dx. And this is going to become minus B square L square V upon M capital R plus small r. And then this V and this V gets cancelled. And what do we have? We have dV is equal to, or we can write dV is equal to minus of B square L square upon small m capital R plus small r into dx. Is that correct? So this is the relationship. Now it becomes very clear that we'll have to integrate this on both sides. Okay, so the limit of integration is going to go from 0 to x. The position is going to go from 0 to x, and the velocity is going to go from v0 to v. The initial velocity, remember, was v0. So the velocity is going to go from v0 to v. Now when we integrate this, this is going to become v minus v0 is equal to minus B square L square upon M capital R plus small r. Everything is a constant. If we integrate dx, we're going to get x after putting the limit. So we are going to get v is equal to v0 minus B square L square x upon M capital R plus small r. Right? So this is going to be the velocity as a function of x. Is that clear? Is this problem clear? Okay, if this is not clear, if there's anything that you want to ask me, please go ahead and I'm going to answer that. Alright, perfect. Now let's go to the next part. What is the next part? Okay, we have found the velocity as a function of x. Awesome. The maximum distance the wire will move. So we figured out that V is equal to V0 minus B square L square x upon M capital R plus small r. Okay, now can someone tell me that how do we evaluate this? The maximum distance the wire will move. Can someone give me a hint how to go about this question? I want to understand from you. Can someone give me a hint how to go about this? What if velocity, V is velocity when it is out of the field? No, Captain, it is given in the question that the rails are very long. Okay, the rails are very long. So we are talking about a situation where the rod is always going to be inside the field. That you can assume. Alright, so in this particular part, what we have to find out is the maximum distance the wire will move. How can we figure that out? Any hints that you can give me? Think about it. The velocity of the wire is, okay, when kinetic energy is 0, When kinetic energy is 0, Captain, we don't have to go to kinetic energy. What makes kinetic energy 0? Arshita is saying Newton's law. Of course we are going to use Newton's law, but I want to know specifically what should we use here. Does it have to do something with the equation of motion? Yes, of course. It has to do something with the equation of motion. Yes, absolutely. Velocity. Now think that this velocity was, the wire was thrown with a velocity v0. The initial velocity was v0 and the acceleration was always towards the left. Okay, so the wire is decelerating. Okay, so the wire is going towards the right, but it is decelerating. What is the farthest distance that the wire can go? When its velocity becomes 0. Okay, when its velocity becomes 0, then it cannot go any further, right? So we are going to have the maximum distance when velocity becomes 0. Do you agree? The wire is going to reach its maximum distance when the velocity becomes 0. Okay, if the velocity becomes 0, we're going to get x is equal to v0 into m, or we get mv0 into capital R plus small r divided by b square L square. Is that right? Okay, so what are we going to get? We are going to get this as our answer. Is that clear? Okay, so this was a slight variation in the motional EMF problem itself. So I hope this is clear. Okay, and guys, if you have anything you want to ask me regarding EMI, regarding these questions, regarding any concept, feel free to ask. Alright, so if this is clear, we are going to take the next question. Alright, so let's go for the next question. Alright, let's see. What do we have here? We have a uniform magnetic field B which exists in a cylindrical region. The magnetic field increases at a constant rate of dB by dt. Okay, so you can see that the magnetic field is in the cylindrical region, and it is increasing at a constant rate of dB by dt. Now consider a circle of radius r coaxial with the cylindrical region. Find the magnitude of the electric field E at a point on the circumference of the circle. This is the situation. Okay, so we have to find out what is the electric field at a point on this circumference. Alright, so the first thing I want to ask from you is, what electric field are we talking about? What electric field are we talking about? We don't see any charge over here. Okay, we don't see any charge over here. We don't see any source of electric field here. What electric field are we talking about here? Can someone explain that to me? So we have to find out the magnitude of the electric field at a point on the circumference. But what I want to understand from you is, what electric field are we talking about? Awesome, awesome, Captain, awesome. Induced EMF. Induced EMF, yes, of course, there's going to be induced EMF. But what electric field are we talking about? Here we are talking about an electric field. Okay, so here we are talking about the induced electric field. Okay, yes, absolutely, Aman. We are talking about the induced electric field. Okay, so when the magnetic field is changing, okay, so there is no motion of the wire over here. There is no motional EMF over here. So you know that EMF can be of two types: motional EMF and EMF due to induced electric field. So here we don't have any motion of the wire, but still EMF is being induced because the flux is changing, the magnetic field is changing, the flux is changing, the EMF is going to be induced. Okay, now this EMF induced is because of the induced electric field. Okay, and how do we figure that out? The closed integral of E dot dl is equal to minus d phi by dt. Is that correct? The closed integral of E dot dl is equal to minus d phi by dt, and this electric field is called the induced electric field. Absolutely, this is called the induced electric field, and this induced electric field is non-electrostatic in nature. Right? So this electric field is non-electrostatic in nature. It is a non-conservative field. So we cannot define electrostatic potential corresponding to it. Okay? For a field which would have been electrostatic and conservative, closed integral of E dot dl would have been 0 for conservative field. Okay, very important concept here. Because work done in a round trip is 0. Work done in a round trip is 0 for a conservative field. So for a conservative field, closed integral of E dot dl should be 0. But here the closed integral of E dot dl is not going to be 0. It is going to be some finite value. Okay, because this is a non-electrostatic field. For a non-electrostatic field, the closed integral of E dot dl can be non-zero. Okay, so now let's talk about it. Okay, now the magnitude of magnetic field is uniform in space. The magnitude of magnetic field is uniform in space and it is symmetrical about the center. Okay, it is symmetrical about the center. What does it mean? It means that I can have a symmetry argument. Okay, I can have a symmetry argument stating that the electric field at all these points, okay, electric field at all the points on the circumference, the magnitude is going to be the same. The electric field magnitude is going to be the same. Is that correct? Because the situation is symmetrical. Okay. The next thing is, what about the direction of electric field? Now think about it. Think about it. Now when the flux is changing, then current is going to, the charge is going to be flowing. Okay. There is going to be EMF induced, and if EMF is induced, then charge is going to flow, which means the current is going to flow. Okay. But what force is making this current flow? What force is making this charge flow? It is the electric field. So if we have an electron over here, okay, and if it starts moving, obviously it is going to start moving along the loop, which means the force should have been along the loop, which means that the electric field is going to be along the loop as well. Okay, so using these two arguments, what we can say is that the magnitude of electric field is going to be the same. The magnitude of electric field is going to be same everywhere. The magnitude of electric field is going to be same everywhere, and the electric field is going to be tangential everywhere. Okay, so these are the two arguments that we have to, using these two arguments, we have come to this conclusion. Okay, so what we have to do is we have to do closed integral of E dot dl. Okay, Captain, which part do you want me to explain again? Let me know. Which part do you want me to explain again? Pratham is asking, sir, current is induced in a loop if the loop is closed, right? Yes, absolutely. If the loop is closed, then the current is going to get induced. Then the current is going to flow. But even if the loop is not closed, EMF will be induced. Alright, direction, Arshita, we are going to talk about the direction very soon. Don't worry about it. What I want to know from you guys is it clear that the electric field is going to be tangential to this loop, and the magnitude of electric field is going to be same throughout? Okay, there it is going to be same through at any point. Okay. Alright, now what we have to do is closed integral of E dot dl. Okay, so what we are going to do is we are going to give a sense to this loop. Now if we have to do dl, now dl is a vector, okay, dl is this vector. We are going to take a small length dl and it is this vector dl, okay. So we have to find the direction of dl. So we have to assign a sense to this loop, okay, we have to assign a sense to this loop. So what I'm going to do is I'm going to assign an anti-clockwise sense to the loop. I'm assigning an anti-clockwise sense to the loop. What does it mean? If I'm assigning an anti-clockwise sense to the loop, let me draw it here, then it means that here the direction of dl is going to be towards the left. Here the direction of dl is going to be downwards. Okay, so basically the direction, the sense that I have given to the loop is going to dictate the direction of dl. Is that right? Okay. Now the second thing is that electric field is going to be tangential at every point. Now I don't know what is the direction of electric field. It is right or it is left. I don't know right now. I can figure that out, but I want to figure that out by Faraday's law. Okay, so let's say I'm assuming that the electric field is in this direction. The electric field is in this direction. The electric field is in this direction. Okay, so what is the angle between E and DL? The angle between E and DL becomes 0 degree. Can you see that? The angle between E and DL becomes 0 degree. So this becomes closed integral of E dl. And this is equal to minus d phi by dt. Now what is phi? Let's say that the magnitude of magnetic field is B and the radius of this loop is R, so the area is R. So what does this become? This becomes minus. Now we have given it an anti-clockwise sense. Think about it. We have given it an anti-clockwise sense. If we have given it an anti-clockwise sense, what we are going to do is we are going to curl our fingers anti-clockwise, and then the direction of thumb is going to give me the direction of area vector. So the area vector is going to come out of the plane. Okay, is this clear? So I'm going very methodically. See, we have to calculate the magnitude, so we could have forgotten about everything. Okay, but I want to do it very methodically, so I'm telling you each and every point. Okay, each and every small thing I'm telling you also. Okay, so what I have done is I have given a sense to this loop. Now the sense of this loop gives me the direction of DL. Okay, the sense of the loop gives me the direction of DL. Also the sense of the loop gives me the direction of area vector. Okay, now this is an open loop. The area vector could have come out of the plane or it could have gone into the plane. Okay, but once we have assigned a sense, the sense is anti-clockwise, so in that direction the area vector is going to come out of the plane of the loop. Is that correct? Alright, perfect. So here this is going to become d by dt of, now the angle between magnetic field and area vector is 180 degree. Can you see that? The area vector and the magnetic field, what is it? The direction, the angle between them is 180 degree. B is going into the plane of the screen, A is coming out. So what does this become? This becomes B into pi r square, but I'll have to put a minus sign also. Is that correct? Is that clear? Okay, now what will happen is E is going to come out because the magnitude of electric field is constant. So we'll have closed integral of dl, and this is equal to, the minus sign will get cancelled, and we have pi r square dB by dt. Is that correct? Okay, minus sign minus becomes plus, and then pi r square is a constant, but B is not a constant. So we are differentiating B with respect to time, so that becomes dB by dt. Okay, now what is dl? Remember, this is not dl vector, this is the length dl. This is only the length dl. So if I add all these lengths, what is it that I'm going to get? I'm going to get the circumference. So this is going to become E into 2 pi r is equal to pi r square dB by dt. Correct? So this r and this r is going to go away, this pi and this pi is going to go away. So finally what I'm going to left with, I'll be left with E is equal to r by 2 into dB by dt. Is that correct? So the magnitude of induced electric field is going to be r by 2 dB by dt. Okay, now the direction of electric field will depend on whether dB by dt is positive or dB by dt is negative. See, so the direction of electric field I have chosen, if dB by dt is increasing, which is given in the question, okay, here it is given in the question that it increases at a constant rate of dB by dt, which means dB by dt is positive, which means electric field comes out to be positive, which means the direction I have chosen is correct. Okay, but let's say in this situation, if dB by dt was decreasing, then dB by dt will come out to be negative, and hence E will come out to be negative. So what will I say? I'll say that the electric field is going to be in the opposite direction. That's all. Okay, but the direction of current, the direction of induced EMF, you can also find using Lenz's law. That's not difficult at all. Okay, that also you can find very easily. Is that clear? Perfect. So this is the first part of the question, and you can remember this result as well. Okay, so whenever you are dealing with induced electric field, it's good to remember this result. It will come in very handy. Okay, now let's go to the next part. Alright, we have done this. Let's go to the next part. Alright, so consider a point P on the side of a square circumscribing the circle. Show that the component of the induced electric field along BA is the same as found in part A. Okay. Now what we have to do is we have to find out the electric field at point P, and the component of electric field along the line BA we are saying is going to be the same as the one found in the last problem. Is that right? Alright, so let's do that. Now what I am concerned is, I am concerned in finding the induced electric field at point P. Okay. Now this point P is not falling on a circle. Now in the previous question what we did was we had chosen a circle, and at all the points on that circle we knew what will be the magnitude of induced electric field. Okay. So very good idea would be to draw a circle which passes through P. Okay, like this. So what I have done is I have drawn a circle which passes through point P, and I am saying that the radius is r prime. The radius of this circle is r prime. Okay. Now this becomes exactly like the problem before. So what I can say is that the electric field at point P, is going to be r prime divided by 2 dV by dt. Do you agree? Now the radius has become r prime. So on this circle, can I say that EP is going to be r prime upon 2 dV by dt? Is that correct? Any problem? Okay. And what will be the direction of EP? The direction of EP is going to be tangential at this point. Clear? Now what I have to do is I have to take the component over here. Okay. So let's say if this angle is theta, this angle is going to be 90 minus theta. So this angle is going to become theta. Correct? So from here, what can I say? What is the component of EP along BA? Component of EP along BA. So the component of electric field along BA is going to become EP cos theta. Do you agree? So this is going to become r prime upon 2 dB by dt into cos theta. Is that clear? Any problem? Perfect. Now what I want you to do is I want you to look at this triangle. The hypotenuse is r prime, this angle is theta, and this is r. So what is r prime cos theta? Isn't r prime cos theta equal to r? R prime cos theta from that triangle is equal to r. So r prime cos theta I can replace it by r. So this becomes r by 2 dB by dt. Is that clear? Okay. So we have found out what is the induced EMF at point induced electric field at point P. We have taken a component along BA, and that comes out to be r by 2 dB by dt, which was the induced electric field we calculated in the last section. Hence we have proved this. Is that correct? Okay. So this is going to become r by 2 dB by dt. Alright, so this is a problem on induced electric field, okay, and there are many good problems which can be formed on induced electric field. Not very frequently asked, but it is a very interesting section, okay. So if you remember this concept, then solving these questions can become much simpler. Alright, so guys, that is it in this session on electromagnetic induction. What I could not complete in this section because of the dearth of time, you can always go back and check. So I could not go for LR circuit, which is a very simple part. So I would strongly recommend you guys to go back and revise LR circuit. And also I want you guys to revise LC oscillation. That was also a part which I could not cover in this session. But LC oscillation is very, very similar to SHM. So just go back, revise it once, and hopefully tomorrow also we have a session. So we might be solving some questions which will cover all these topics. Yes, absolutely. Self-inductance. So when I say LR circuit, I mean along with that self-inductance, mutual inductance. That is the part we could not go for, but probably in the next session we'll be able to solve a few questions. But you guys should always go back and revise the concepts that we could not do in this particular session. Alright, it was so much fun doing this session with you guys. Such an interactive audience, such an enthusiastic audience. Absolutely love this session. I hope this was helpful for you. So, we're going to meet very soon in the next session. But till then, keep practicing, keep getting better, and have fun with learning. Thanks for watching.